Okay, so picking up the threads from last time. So we talked about what exactly is a shock wave, right? And how the disturbances travel through the medium. And we also used the governing equations and applied it for a normal shock and saw how the governing equations look like. Okay. Now the next question is that every time we talk about shock waves or compressible flows or gas dynamics, we constantly talk about the Mach number, right? High Mach number flows and things like that. So I think I said last time that we'll see why, right? What is the connection of Mach number now with compressible flows? So let's see what exactly is the relationship between the speed of sound, right? And why are we talking about that in context of shock waves? Okay. Now let's see what is the relationship of speed of sound. So now let's just okay. Now without going into the derivation of this, so we have a relationship like this, right? Now A here is the speed of sound, okay? A here is the speed of sound. P is pressure and rho is density, and if you remember correctly, this is entropy, right? And if I write something like this, then del P del rho at constant entropy, which also implies that I'm talking about an isentropic process, right? What this essentially means is that, or if I may, this is kind of easier for me to visualize. Right? So this is a unit change in density per unit change. This is a change in density per unit change in pressure, right? So, and this change is happening over constant entropy. So that process of change is isentropic. So that S is basically entropy, and the process here is isentropic. Okay, so that is essentially the relationship. So A square is equal to this, or if I may write this, okay. Now if you can recall some of the derivations or the definitions that we did last time, could we write this in another form? Could we write del P by del rho in another way? Well, think about this. Now, okay, now V here is the specific volume, and tau S, if you remember, is the compressibility or isentropic compressibility, okay? Okay, so S denotes, so tau S basically says isentropic compressibility, right? Now, so therefore now this kind of gives us some idea, some relationship between the compressibility of a gas and the speed of sound, right? And if you remember what the definition of the compressibility was, it was the fractional change in volume per unit change in pressure, right? So now, so essentially what we are trying to say here, if I were to take this definition, right, and ask a couple of questions, so like we said yesterday that, we are looking at, say, this point. Say we are looking at this point, right? And you are, say, traveling from here. So you are traveling from here, right? You have a certain speed, right? The example that I gave in last class was that, there are a group of people standing over here, you are riding a bike, right? And then you ring your bell. Now say you have a certain disturbance, right? Because of you whizzing past, there's a certain disturbance. Now depending on the speed at which you are traveling and the speed at which these disturbances are traveling through the medium over here, and the medium of travel over here is air, right? We will have a shock wave or not have a shock wave, right? Now if these disturbances are traveling faster than you, right, so they reach this area, yeah, they reach the area, and then this point here is able to then it almost gets notified that okay, there is this person coming, so I need to adjust myself, right? So then you have, then it adjusts itself, and so there is a certain change in pressure, temperature, etc., right? However, if you are traveling so much quicker than these disturbances that you reach way quicker than these disturbances can reach over here, then this has to suddenly adjust itself, and that's when you get a shock wave, right? Now the question is that, so therefore now just let us just look at the disturbances traveling, right? These disturbances traveling through the medium over here, right? And let's say these are causing a shock wave. Okay. Now the question is that now if these disturbances are traveling through air, they travel at a certain speed, right? Now what if I change this medium? What if I change this medium? If I change this medium to another gas, or for example, make this a slightly heavier gas, okay, or if I make this slightly lighter gas, then what happens? Do the disturbances get affected or don't they get affected? They'll travel anywhere at the same speed, right? Now the crux of, to answer that question, the crux of the matter is that now sound waves, right, sound waves are material waves, unlike electromagnetic waves like light. So they need a medium to travel, hence they definitely depend on the type of medium that we are traveling in, right? And the quantification that we just did, that the speed of sound is, so therefore this is the compressibility. So this affects the speed of sound, the compressibility, right? So which means if the compressibility is more, if it is more compressible, the speed of sound will be less. So that is essentially the relationship between the sound waves. Okay. Now again, we still need to answer the question that what is the connection of then sound waves with these disturbances in the atmosphere, okay, in any medium for that matter. Okay. Now they are kind of related to the mean molecular velocity. Okay. We will not go into the exact relationship of that, but let's just say that these sound waves are somewhat related to the mean molecular velocity, right? And when these disturbances travel, they're basically traveling, say, from this point to this point by passing on that information from one molecule to the other, right? So essentially these molecules are being disturbed, right? And therefore these disturbances, hence these disturbances, perturbations, whatever, they travel from this point to the other. Okay. So and therefore we use sound waves as a measure of finding out how fast these disturbances will travel, right? And hence the Mach number is such an important factor when we talk about compressible flows. Okay. All right. Now there is yet another way that I can represent the speed of sound. Now if I consider, okay, having say written this, so we have one quantification, right? We have one quantification, and that is the relationship of speed of sound with the compressibility, right? Now if I consider isentropic, which is adiabatic and reversible, right? So if I consider isentropic, then we can get this sort of this is the relationship if I consider isentropic. Okay. Now if I do that, now I have also defined as an isentropic relationship this way, right? Now instead, so now in this relationship over here, del p del rho, if I can use this expression over here, what I get is something like this. Right, and therefore I can actually therefore again write okay, so I can actually also write this as now we will see how we will use this relationship. Okay, we will do a couple of problems and then we will see how we will use this. So what we've done now is basically relate the speed of sound with the compressibility, and you can see that is also related to the temperature, right? So okay, having said that, so then of course you know that the Mach number is speed by velocity by speed of sound, right? So Mach number is v by a, and then we say subsonic, sonic, and supersonic, depending on whether the Mach number is less than 1, equal to 1, or greater than 1. I think that's something you know already. Okay. I think what we will do now is do a couple of problems and see if we can put these relations into practice, okay? And some other relations which we derived a couple of classes back, I think. Okay, so let's start doing that, okay? Now, so we have a pressure vessel which is which stores high pressure air for operating a supersonic wind tunnel. Right. So what we have is a vessel like that. Okay. Now what we do is we store air over here at a this is the volume, okay. So what we have here is that we are storing air in this vessel at a very high pressure, which is 20 times the normal atmospheric pressure. So 20 atmospheres. It has a volume of 10 meter cube, and it is at a temperature of 300 Kelvin. Okay, and we use this to operate a supersonic wind tunnel. So what does that mean? So basically what I'm going to do is make it run through a, if you remember this, so basically we're going to make it run through here, right? Pass this gas through here, make it undergo some changes, right? There will be some changes here, and that's what we're going to find out. Now what sort of changes is required to get this air in here, which is stagnant, right, here, to go through this, to pass it through this tunnel so that it comes out with a Mach number which is greater than 1, right. So what changes in its properties do we need to make this air to now become to be traveling at supersonic speeds? Okay. So what we do now is we heat this gas, right. Now this gas is heated to 600 kelvins. Okay, it is heated to 600 kelvins. So what the question to be answered is, what is the entropy change? Right? What is the entropy change? So essentially this is what we are looking at. So what is the change in the entropy? Okay. So so again, so basically we have stored gas here. We're going to run it through a wind tunnel, and this gas is going to then travel at speeds higher than Mach number. And during that process, there will be an entropy change, and we want to find that. Okay, so that is the problem here. Now, how do we go about doing this? Okay, so let's start. Okay, let's start with this relationship. So PV is equal to RT. That's the basic gas equation of state, right? Now, what happens to the volume over here? This is a chamber. This is a vessel. Okay, now this will always will have very strong steel walls, right? So this volume is not going to change, right? The volume remains constant, isn't it? So therefore, if I can write this, or basically what I am saying, this is the universal specific gas constant. So essentially what I am saying is this is constant, right? For this particular process, P by T is constant, right? So now let us say that these conditions is condition 1. Let us say that these conditions, which is the stagnant conditions, is 1, and when it becomes supersonic finally at the exit, let us call those conditions as 2. Okay. So say this is how it is traveling, say. So here say Mach number is greater than 1, this is at the exit of the tunnel. So let us call this as, let us call the properties over that as 2, right. So what this essentially means is that is this, right, isn't it? Or we can write this as, or we can say isn't it? Now, P2 is something that we do not know, right? P2 is the pressure at the exit, and P1 is given. P1 is 20 atmospheres. Now, T2 is known, which is 600 Kelvin. T1 is also known, which is 300 Kelvin. So therefore, okay, so we get this relationship. So let's mark that. Okay. All right. The next thing is we need to find the entropy change. Okay. Now, if I have to find the entropy change, what is my relationship? What is the? So again, S2 is here, and S1 is at the stagnant conditions in the vessel, right. So this is equal to right. So in this relationship we see that we know T2 by T1, which is 2, and P2 by P1 is also 2, right. And we know the specific gas constant, this is 287, this is the standard constant, right. Now, we need to find out Cp, right. We need to find out Cp. Now, how do we go about doing that? If you remember the relationships, for example, Cp minus Cv is R, right. So Cv is R by gamma minus 1, and so therefore you can combine these two. So in there, if you take If nothing is specifically given, you can take the gamma as 1.4, right. If you do that, then you can find Cp from here, and R is 287, right, here. So 287. Now if I do this, okay, so I know the value of R and I know gamma, so I can find Cp from this, right. And if I do that, then I get a value of Cp which is okay, you can check that. Okay, so it's essentially I'm just putting these values in here and I get Cp. Okay, now once I do this, I should be able to get my change in entropy, right. Once I've done this, I should be able to get the change in entropy, which now means that so okay, let me just write this out. So this becomes Cp is 1004.5, the natural log right, that. So we get this. Now this comes up to be, what I get here is 497.3 joules per kg Kelvin, right. So what we get here is the entropy change for which is around 500 joules per kg Kelvin. Okay, so we got some answer for this. And so in here, so this is say around 500 joules per kg Kelvin. So as you can see, this is basically specific entropy, right. So we are defining that by over the unit mass. So okay, now so we would really like to know what is the total entropy change, isn't it, because we have a total volume of gas to be 10 meter cube, right. So for that we get a specific entropy as 500 joules per kg Kelvin. So what is the total mass here, mass of gas, so that we can calculate the total entropy change, right. And why is the entropy change important, and why should we be concerned about the entropy change? Let's answer that question. Let's find out first the total entropy change. Okay, so to do that, to get the total mass of the gas, we need the volume, which is given 10 meter cube, into what? Into the density. And how do I get this density from? Right? This is what I need, the density, right? Now we will again use this. Right. Now this is the specific volume, isn't it? This is for unit mass. So I can also write this as isn't it? I think you should be able to figure out why, because see, density is mass by volume, right? So when you say volume as this V, this is specific volume, that means the mass is 1 unity, right, because this is volume per unit mass. So therefore this, if this is V, then this is 1. So that's why I can write V as 1 by rho. If I write that from here, then I get rho to be, this is my density, right, this is my density of the gas, and this we can find because pressure is given to be 20 atmospheres, right, 20 atmospheres, and temperature is 300 Kelvin, right. So this pressure is 20 into this is Newton per meter square, right. So this is the total pressure, this is specific gas constant, and T is the temperature. So these are the conditions under which the gas is stored in the vessel, right. So the density of the gas in the vessel, which is not explicitly given, can be calculated. So this is your rho, and okay, I didn't calculate that explicitly. You can get it separately if you want. So therefore, the mass of the gas therefore is this this rho into the volume, which is into 10, right, and that I get as 234.6 kgs. So which is say around 235 kgs. So we get 235 kgs of gas, right, that is being stored in the vessel. Therefore, the total entropy change, so which is, say, if I write that as caps S, would be say around, so I had around 500 joules per kg Kelvin into 235 kgs. So I kind of get, you know, this is, I get around say 1.2 into 10 to the power 5 joules per Kelvin, right. So this is the total entropy change for the given mass of gas, right. So therefore, like I asked the question that why is this important, right? Why is the entropy change important? So basically what we are seeing is that we have a gas which is stored in a vessel, right, at a certain volume, temperature and pressure, and as a result of which it has a certain density, right. And then we heat the gas, I make it travel through the tunnel, right, and there is an entropy change. There is an entropy change of nearly 500 joules per kg Kelvin, and total is around 1.2 joules per kg for the given mass, and I get supersonic speeds, right. Now, why, however, I need to know this? Is this information important? You know, why are we sitting here and calculating all this entropy change and so on and so forth? Now, if you remember the definition of entropy, so the entropy change gives us a measure of the heat generated, right, the heat or the heat generated, in this case heat generated or heat required, right. So it's directly proportional to the heat generated. So therefore, we will have the total entropy change will give us an idea of how much heat is going to be generated when such a process takes place, right, and this information is important, right. So okay, so that was one example, right, where we were able to use, you know, basically as simple relationships of these relationships of, you know, for an isentropic process, and we were able to find out the, you know, total entropy change when we were trying to run a supersonic wind tunnel. Okay, let's take another problem and then try and understand a little more. Okay, so now the next problem would be, now let's consider the flow. I think we'll be doing this quite a lot now, you know, try to understand flows through nozzles, etc., right. So we'll try to consider the flow through a nozzle. So we will consider the flow through a nozzle, and there are two considerations given, right. So basically when we say a nozzle, right, the gas is going to expand through the nozzle like we did in the previous example. So we will consider that process to be isentropic. Isentropic expansion of the gas. And secondly, we will consider the gas to be So what this essentially means in terms of solving a problem is that we have a handy equation. The moment I say isentropic expansion, I have a handy equation. The moment I say calorically perfect, we have a handy relationship, right? Okay, but time and again I think we should remind ourselves what exactly we mean by isentropic or calorically perfect. I think once we keep doing that, it kind of justifies the relationships and the equations that we use, right? Okay. So therefore, now therefore we have the chamber, right? We have a chamber where we have fuel and oxidizer, right? So they burn. So basically, the gas and the oxidizer, they burn and create the fuel. Now the fuel is generated in this chamber, right? So this is the fuel chamber, right? And this here again, the pressure is 15 atmospheres and the temperature is, okay. Then the molecular weight is 12 and the Cp is also given to be okay. So this is the fuel which is being stored at these conditions, right? And this now expands again. So again we are going to run the nozzle. So at the fuel here just before entering the nozzle is at these conditions, and at the exit of the nozzle, at the exit nozzle, the temperature is 1350 Kelvin. So what you see is that the fuel is being generated at 2500 Kelvin, right? And at the exit there is a drop in temperature to 1350 Kelvin. So there is a quite a large drop in temperature, right? So what we're going to basically ask is that what is the pressure? What is the pressure as the exit? For this change, change in the temperature, what is the corresponding drop in the pressure, right? So how do we go about solving this? Okay, so what do we need for this process? Now one thing is that let us see, now we said it is isentropic, right? So now the change is isentropic. So let us use these relationships. So the relationship is okay, so this is the relationship. So basically all we need to do is plug in our values into this relationship and we should be able to get P2, right? The subscripts again say, let's say the the fuel chamber is 1, so these are 1s, and at the exit is 2, right? Now the exit temperature is known, the inlet temperature is known, the pressure is known. All we are asking is what is P2, right? So we just need to plug in our values into this and we should be able to get the exit pressure. Now before we do that, what we need is the value of gamma, right? Now unlike in the previous case where we took that as just as 1.4, here Cp is given. Cp is given over here. So what we need to find out is Cv, and then we will take a fraction of that, like Cp by Cv, and that's what will give our gamma, right? And how do we do that? Again we will use these relationships. Right, this is a specific gas constant. So this is the specific gas constant, right? So that this specific gas constant is, this is the universal gas constant, okay, by some mass, right? Now, what mass is this? I think we talked about this a little bit in detail in the first class, right? So this is the specific gas constant which we need over here, right? And so this is the universal gas constant, this is the mass. So in this case, this is given. This is the molecular mass which is given, and this is the standard value which we will use, 8314, I think, right? 8314, and this is the molecular mass. So therefore, we will get the specific gas constant. Okay, so I hope you're beginning to see why we use these these expressions for specific gas constant or specific volume, etc. What is the significance of that? Because especially when we are considering different gases with different molecular weights, that's when we talk about specific gas constant or specific volume, because the same number of molecules of different gases will weigh differently. Okay, the mass of the same number of molecules, the Avogadro number of molecules, will weigh differently for different gases. So if you change the gas, like we saw in the previous example, right? So the density is not going to remain constant, because that will depend on the pressure, temperature, etc. At the same time, if you change the gas itself, right, now these values also start changing because the molecular mass is changing. So in this case, the molecular mass is given as 12. So therefore, now this value here becomes, this R is joules per kg Kelvin, which is unlike, it's nearly 693. This was 287 in the previous case, just to bring out the differences. So once you get this, Cp is known, so therefore we can get Cv, right? We can get Cv, and that Cv is basically Cp minus, just we write that, and that what we get is 3464 joules per kg Kelvin, right? Once we do that, then we should be able to find out our gamma, right? So in this case, the ratio of specific heats therefore become okay, so gamma is Cp by Cv, right? So which is okay, so and that is 1.2. That is 1.2. So once we get that, then for this particular isentropic process, we will again use this. So we just need to find out we'll just plug in the values now. Okay, so P2 is what we need. P1 is 15 atmospheres, right? That is equal to T2, which is a 1350, and T1 is 2500, and this is gamma by 1.2, that, right? Now if I do this, what I essentially get from here is that P2 is equal to 0.372 atmospheres, which is around 0.4 atmospheres. So this is essentially my P2. Okay. Now what's interesting is, now let us just sort of take a step back and look at all these properties. So what did we do? Okay. Now we have a nozzle, right, and then we are burning a fuel, making that fuel run through that nozzle. Right. Now, when the fuel is generated, it has these conditions. It has a molecular mass of 12, it's a pressure of 15 atmospheres, temperature of 2500 Kelvin. Cp is given. Now, when we run this through the nozzle, at the exit there is a temperature drop which is 1350, right? And see the corresponding pressure change. The pressure change is less than half atmospheres, right? So you see the large pressure change from 15 times the atmospheric pressure. We actually come down to 0.5, less than 0.5 atmospheres, right? So therefore, when I run this, so if you right, so pressure here is 15 atm, the temperature is 2500, and the pressure here is 0.4, actually it is less than 0.4, and T is 1350 Kelvin. Sorry, Kelvin. Okay. So basically, so in the nozzle, so therefore you can see the physical change here. So you can see the physical change here, that to move from but once it moves from here, right. So we have a temperature drop of which is quite significant, which is 2500 to 1350, and look at the corresponding pressure drop. Right. So like we spoke in in the previous lectures, etc., what exactly does a nozzle do? That it brings about a so now think about this, that if I bring about a pressure change which is say 15 atmospheres to 0.5 atmospheres say, then I'm going to get there is a corresponding temperature drop as well, but I'm also going to get supersonic flow through it. Right. So, I mean the two ways to sort of look around this. Okay, I think we will kind of stop here, and where we will pick up the next time, I think what we will start looking at is the way we looked at the relationships using the governing equations, right, for a normal shock wave. Now we will see if we can use those and for a nozzle, especially for a nozzle, and how best we can use those equations to study flow through nozzles, right. Now let me just sort of briefly start that process, and we will pick it up in the next class as well, right. Since we've talked about nozzles over here, I think it's we can just sort of introduce that over here. Okay, let me just go back right here. Now, so therefore in the nozzle, so as you can see here, the fuel is stagnant, right. The fuel is stagnant in this case. So this is we can call this chamber or this condition of the gas to be reservoir conditions. Okay, so if I do that, so say this is my nozzle, right. So this is my nozzle. So now here just before the flow it actually starts happening, now I'm going to call these as reservoir conditions. Right, and these are going to be denoted by a subscript naught. Okay. Now, if you remember the relationship that we developed from the energy equation for a for a normal shock wave was this. Yeah. So we said basically right. So what this again 1 and 2 basically in here. So this is the relationship that if the flow is moving from say 0.1 to 0.2, right, 0.1 to 0.2. So it could be anywhere, this could be 0.1 and this could be just 0.2. Right. If it is so the relationship between the enthalpy, the velocities and the heat is this, right. Now let us consider this as isentropic. So we are left with this. So therefore I can bring this down and say that this is constant, right. So if I do that, this is constant. Now let us define this constant now. Let's say this one, or say this one, this location 1 is the reservoir, So, if it is a reservoir, U there is 0, right. So, therefore, we have H is equal to constant if I have the reservoir condition, and like we said, we will denote this specially. So, we will denote this as H naught, right. So, therefore, in the reservoir, therefore, so now my, so this is my 1. So, my conditions, therefore, this is H naught, then the corresponding T naught, rho naught, V naught, and so on and so forth, right. So, this is essentially H naught. So, these are the this is the notation. So, every time you see something like this, right, every time you see something like this, you will know that we are considering basically the reservoir where there is the flow is stagnant, okay. There is essentially no stagnant conditions. So, this is a special kind of denotation, like and the corresponding again. So, if I had to calculate the speed of sound, then now the speed of sound is again given by, right. So, if I consider the reservoir, then I am going to call this as right. You are going to call this as this, and yeah. So, this is the condition. So, therefore, this is the reservoir conditions, or total conditions actually, because after this, when you are going to expand this or accelerate this through the nozzle, there is going to be a temperature change, pressure change, etc. So, these are the reservoir conditions, and the special denotation with naught corresponding is this. So, now in the nozzle usually, right, the way we would kind of define this is here it is say subsonic, it's kind of more or less kind of defined like this. So, now this area more or less sonic zone is actually kind of, you can say that this is kind of the throat, right. Now, in this case we can denote these values whatever we define here with a subscript naught, we will define those values on the throat with a superscript star, meaning I will denote that as say H star, P star, T star, rho star, etc. Okay. So, I guess we will just stop over there, right, and we will develop this relationship again for the nozzle, and see how we will basically what we will do is develop the relationships in terms of, and see if we can introduce these values somewhere into the relationship, in the sense that if I have values like this. So, basically if I have any condition in any point over here, say if I have a point over say section over here A, right, or I have a section over here, right, say B. So, I will try to find out these values at the properties at A and B with respect to say the reservoir conditions and the throat condition, then we will see what is the usefulness of that, why do we need to do that. Okay. So, all right, we will stop there and we will continue this in the next lectures. Okay. Thanks.